In this video, we will work an example evaluating the work in a polytropic process. For this problem, the polytropic constant will be 0. Recall that when n equals 0, we have a constant pressure, or isobaric process. Let's imagine a piston cylinder apparatus that is connected to a large supply air tank. The pressure of the air in the tank is 3000 psi gauge. The atmospheric pressure is 14 psi absolute. The volume of the tank is 10 cubic feet, and the temperature is 70 degrees Fahrenheit. The cylinder has a diameter of 3 inches and an initial length of 3 inches. The piston moves 3 inches such that the system expands. Thus, work is done by the system. This apparatus finds many practical uses, such as in heavy pneumatic machinery. An example could be a pneumatic press in a factory. Let's compute the work. First, we define our system and compute the initial volume. The system is all of the gas in the tank and the cylinder. The initial volume of the cylinder is the area times x1, which is equal to pi r squared x1, which is equal to pi 3 over 2 inches squared times x1, which is 3 inches. This equals 21.195 inches cubed. We can convert this to cubic feet. You see that the inches cancel, and we're left with 0.0123 cubic feet. The initial volume of the system, neglecting the volume of the hose, is the sum of the tank volume and the cylinder volume, which is 10 cubic feet plus 0.0123 cubic feet. This means that the initial volume is 10.0123 cubic feet. The final volume of the cylinder, V2 cylinder, is equal to the area times the new length, which is x1 plus delta x. This equals pi times r squared times x1 plus delta x. Substituting, we get pi 3 over 2 inches squared times x1, which is 3 inches, plus delta x, which is also 3 inches. This equals 42.39 cubic inches, which once again we can convert to feet. Find the V2 of the cylinder is equal to 0.0245 cubic feet. To compute the final volume of the system, we have to add the volume of the tank. So V2 is once again the volume of the tank plus the volume of the cylinder at state 2, which is 10 cubic feet plus 0.0245 cubic feet. So V2 is equal to 10.0245 cubic feet. Remember that V1 was equal to 10.0123 cubic feet. So here we see that the volume changes very little relative to the pressure in the supply tank. We can assume that the pressure in the supply tank does not change significantly. Thus, we can model the process as isobaric. Recall that the work done when a system changes volume can be computed from the integral of pressure over the volume change. Work is integral from volume 1 to volume 2 of P dV. For a polytropic process, PV to the n equals a constant. For a constant pressure process, N equals 0. Substituting, you get PV to the 0 equals a constant. In other words, pressure equals constant. Substituting into our work integral, work is equal to the integral from volume 1 to volume 2 of P dV, where P is a constant, so the pressure comes out. We're left with the integral from V1 to V2 dV, which is simply pressure times volume 2 minus volume 1. Remember that we must use absolute pressure when multiplying or dividing. The work then is equal to the pressure, 3,000 psi gauge, plus atmospheric to get absolute pressure, times the change in volume, 10.0245 feet cubed, minus 10.0123 feet cubed. Notice that we're multiplying pounds per square inch by cubic feet, and so we must convert. The conversion is times 12 inches per foot times 12 inches per foot, so the inches here cancel, and we're left with pounds per square foot. Multiplying this out, we arrive at 5,295 foot-pounds force. We can convert this result to British thermal units by multiplying by 1 BTU is equal to 778.17 foot-pound forces, which is equal to 6.8 BTU. As a side note, let's compute the final temperature of the air in our system. We can write the ideal gas equation of state for each state. P1 V1 equals M1 R T1. P2 V2 is equal to M2 R T2. We recognize that for a closed system, the mass must be equal. Thus, we can solve for M and equate the two. Remember that we are assuming that pressure remains constant. Thus, the pressures cancel. Also, the specific gas constants cancel. We can solve for the temperature at the final state, which is just equal to T1 times V2 over V1. Remember that we must use absolute temperature when multiplying or dividing, so we have to convert T1 to absolute temperature. The result is that T2 is equal to 70 degrees from our problem statement, plus 459.67 degrees Rankine, times V2, which is 10.0245 feet cubed, divided by V1, which was 10.0123 feet cubed, where T2 is 530.315 degrees Rankine. Subtracting 459.67, we can convert to Fahrenheit. We find that T2 is equal to 70.65 degrees Fahrenheit. We see here that the final temperature is greater than the initial temperature of 70 degrees. This result tells us that in order to achieve a constant pressure work process, we would need to add energy to the system by heat transfer. In summary, we computed the work done in a constant pressure polytropic process. We first computed the initial and final volumes of our system. We then computed the work done by integrating the pressure-volume relationship for a polytropic process, remembering that for a constant pressure process, the polytropic constant is 1. We remembered to use absolute pressures when we were multiplying, and so converted the gauge pressure in the tank to absolute pressure by adding the local atmospheric pressure. We arrived at a value of 5,295 foot-pounds force, which is the work of a 5,295 pound force acting over 1 foot. We computed that this result is equivalent to 6.8 BTUs. Finally, we practiced the use of the ideal gas equation of state by evaluating the temperature of the gas at the end of the process. We noticed that the final temperature was higher than the initial temperature, telling us that we would need to add energy by heat to maintain the constant pressure in this process. This concludes the example. Thanks for tuning in and have a great day.